Hello everyone, I'm Tong from Tsinghua University. The work I'm going to present today is about combating link dynamics for reliable LoRa connection in urban settings. This is a joint work with Zilin Shen, Professor Jiliang Wang, and Professor Yunhao Liu, all from Tsinghua University. Recent years have witnessed the emergence of LoRa as a promising network mechanism to connect IoT devices. Typical LoRa devices can communicate over up to 10 kilometers, and a battery-powered LoRa node can work for nearly 10 years. LoRa works on the unlicensed sub-GHz ISM band. This brings users great convenience in deploying their own LoRa networks. The key point of LoRa is to modulate data using chirp spread spectrum at the physical layer. CSS generates symbols as up chirps, whose frequency increases linearly. It shifts the initial frequency of up chirps for encoding different data bits, as shown in the red line. Then, at the receiver side, the LoRa gateway adopts the chirp processing for decoding. It first multiplies the receiver chirp with a standard down chirp as the green line, and then applies the FFT on the dechirped signal. Therefore, it can concentrate the chirp energy at the shifted frequency on the spectrum and decode the data bits by detecting the energy peak. In terms of long-range and low-power communication, LoRa can separate the energy of the noise by focusing the energy of target chirp on the spectrum. However, as the SNR gets lower and lower, the energy peak can be distorted or even overwhelmed by the noise, making the chirp undecodable. We plot the chirp symbol error rate and packet delivery rate with different SNR conditions and different SF configurations of LoRa. Generally, a larger SF enables lower SNR threshold. This results in a more extended communication range with higher energy consumption. As we can see, the standard LoRa demodulation method determines an SNR threshold under which chirp symbols cannot be decoded reliably. So in this paper, we focus on the problem that LoRa links in urban settings suffer remarkably from dynamic environments. The environmental changes of urban scenarios have a strong influence on the wireless propagation path, which significantly impacts the reliability of long-range LoRa links. When the SNR of the received signal falls below the threshold of the lowest LoRa data rate, the data rate of the link reduces to zero and the device disconnects from the network. Given the relationship between SNR threshold and link reliability, weak signal decoding has been a hot research topic in all fields. For example, some works adopt the cloud radio access network for exploiting the spatial diversity gain on weak signal decoding. They require up to 8 collaborative gateways for collecting and offloading physical samples to cloud servers. However, the multi-gateway collaborations and cloud assistance incur non-negligible costs for system deployment. Another idea is to coordinate multiple LoRa sensors to transmit coherent data and thus can reach a remote LoRa gateway. However, the concurrent transmission requires identical or similar sensing results on multiple near sensors. And the receiver has to be specially crafted to decode the concurrent transmitted LoRa packets. The recent work proposes a learning-based weak signal decoding approach that pushes the lower SNR threshold by designing a neural network enhancer receiver. However, running the DNA model on the low-cost commercial LoRa hardware is very challenging due to its high computation overhead. To summarize, all approaches aim to recover original coding information from the received weak LoRa signals. They do not address the fundamental trade-off between SNR gains and deployment costs, making them unsuitable for cost-LoRa deployment. So in this paper, we propose Falcon, a physical layer mechanism to enable communication links to low SNR disconnected LoRa clients. Falcon aims to provide standard compliant communication for low SNR clients using the cost LoRa devices. It relies on the commercial LoRa transceivers without collaborative receivers or hardware modification. Falcon is also orthogonal to existing weak signal decoding mechanisms. At the heart of Falcon, we reveal that LoRa chirps that are too weak to be decoded by normal dechirp can cause interference to other LoRa transmissions. Recall that LoRa receiver demodulates chirps by identifying the highest energy peak in the frequency domain. A successful demodulation requires the peak to be higher than any other noise peak as the red arrow in the top figure. Otherwise, the receiver incorrectly picks up the highest noise peak as a decoding result, and this leads to symbol errors as the purple arrow in the middle figure. However, signals drowned in noise still have an impact on the channel. When a weak chirp and a bass chirp transmit off the same channel simultaneously, the peak of the weak chirp can introduce cancellation on the peak of the bass chirp, making the latter unresolvable. Based on this, we present the system design of Falcon. First, a bass signal transmitter, either a LoRa client or gateway, delivers LoRa packets to a remote LoRa gateway with adaptive transmitting powers, meeting the lowest signal demodulation requirements. Then, a Falcon transmitter, which cannot reach the gateway, detects the bass signal and switches to the active interfering mode. The Falcon transmitter first synchronizes its time and frequency with the bass signal. Then, it either does nothing or corrupts the bass signal. If the Falcon transmitter does nothing, the packets of the bass signal are successfully decoded as a gateway. Otherwise, the bass signal should have a low SNR and is even undecodable. In this way, Falcon transmitter can successfully convey its data to remote LoRa gateways by selectively corrupting the bass signal. Finally, the receiver can decode the conveyed data by interpreting the interfering results. For the following, we introduce several key challenges in designing the main aspects of Falcon's architecture. The first challenge is how to detect the bass signal. We use a LoRa CAD mechanism for bass signal detecting. Its main idea is searching for strong cross correlation between received samples and a locally generated bass upchirp, and reports a chirp detected signal when the cross correlation exceeds a predetermined threshold. LoRa CAD concentrates the chirp energy through the cross correlation, and thus it works even under the extremely low SNRs. However, when put LoRa CAD for chirp detection in practice, we observe a significant accuracy degradation for detecting the payload chirps. We estimate the CAD error rates by counting the number of successful detections, as shown in the right figure. The SNR requirement for detecting the payload chirps is obviously higher than that of detecting preambles. We reveal the reason for such CAD behavior is due to the frequency discontinuity for payload chirps in a correlation window. So we propose a payload manipulation approach for settling this problem. We design a packet whose payload consists of continuous upchirps as the bass signal. Therefore, CAD can detect the bass signal robustly even during the payload transmission. The second challenge is how to efficiently synchronize time and frequency between Falcon transmitters and the bass signal transmitter. For effective LoRa interfering, each pair of Falcon interfering chirp and bass chirp should be demodulated into the same FET bin, making the two peaks interfere with each other. Synchronization errors will lead to peak mismatching in the frequency domain, and this leads to unsuccessful peak interference. We present a reception-based approach to synchronize both the time and frequency of LoRa transmissions. To initialize the synchronization, the bass signal transmitter first acquires the media and transmits bass signals. Upon detecting the reference packets, the Falcon transmitter switches to the active mode and adjusts its local time and frequency. Falcon estimates all sorts of time delays and frequency offsets on commodity devices. And finally, the Falcon transmitter compensates these delays and offsets by adjusting its transmitting time and radio frequency to achieve a high synchronization accuracy. The third challenge is how to interfere with the LoRa chirps of the bass signal. LoRa chirps are designed to be interference resilient due to the benefit of spreading spectrum. Through dechirping and FFT, the energy of the LoRa chirp is concentrated as a single FFT peak, while the energy of the non-chirp interference will be displayed over the whole spectrum. Falcon transmitters interfere with the LoRa chirps by superposing the bass signals with interfering chirps of the same SF and BW at the same channel. Therefore, when performing dechirping and FFT at the receiver, the energy of the interfering chirp is also concentrated, and thus it can introduce effective interference. Beyond that, to effective packet interference, the interfering signal should have an opposite phase to the bass signal. So we introduce a frequency hopping-based approach for manipulating chirp phases on low-cost LoRa devices. Commercial LoRa devices support frequency hopping by a hardware interrupt, which enables LoRa transmitters to select and switch to a new radio frequency at the interval of each payload chirp. Based on the frequency hopping, Falcon transmitters linearly vary the center frequency of chirps in the interfering packet. This introduces a simple varying initial phase for each interfering chirp. Thus, given the received chirps with arbitrary initial phases, Falcon can generate interfering chips with the offside phases and cause effective packet corruption. Now, let's move to the implementation and evaluation of Falcon. We perform both indoor evaluation in buildings and outdoor experiments at the campus. We adopt the commercial LoRa sensors as the best signal transmitter and Falcon clients. We use the USIP gateway for analyzing synchronization errors and evaluating packet corruption efficiency for Falcon. And for system evaluation, we use the commodity Raspberry Pi-based LoRa gateway with same tech called LoRa chips. In terms of evaluation metrics, we care about the packet delivery rate and symbol error rate for the data link under different SNR conditions. And we also evaluate the SNR gains for SNR threshold when the symbol error rate reaches 20%. All these gains are computed based on our baseline, the Detroit-based standard LoRa demodulator. We first answer the question, how well does Falcon corrupt LoRa packets on the different level of SNRs? We estimate the packet delivery rate under different SNR conditions. We focus on the SNR boundary when the packet error rate for the base signal exceeds 20%. As you can see, when there is no Falcon interference, the SNR boundary for the base signal is negative 25 dB. Then, when superposing with Falcon interference, the SNR boundary of the base signal increases significantly. For example, in this figure, when superposed with interference, the SNR boundary of the base signal increases up to 4 dB, showing the low SNR Falcon interference can cause effective packet corruption on base signal transmissions. The second question for the evaluation is how much does Falcon push the SNR boundary compared with standard LoRa demodulation? We first estimate the symbol error rate of Falcon transmissions under different SNR conditions. We set the SER of standard LoRa for SF12 as the baseline. The left figure shows the Falcon can significantly push the SNR boundary compared with the baseline, and the Falcon transmissions assisted by weak base signals perform much better than those assisted by strong base signals. The right figure shows the SNR boundary for Falcon with error correction and retransmission mechanisms. We also use the SNR boundary for standard LoRa at SF12 as a baseline. The evaluation shows that cooperation with retransmission significantly improves the performance of Falcon, as it can improve the tolerance for link dynamics. When using 5 transmissions representing each one Falcon bit, the SNR boundary of Falcon can reach about 7.5 dB improvement compared with the baseline approach. The third question for the evaluation is how much does Falcon improve the coverage of LoRa gateways in the urban settings? We use trace-driven simulations to show the advantages of Falcon in extending the coverage area. To perform the evaluation, we first estimate the signal power for each position with a land cover map based on path loss model. Then, we calibrate the model using more than 10,000 real collected points with GPS-equipped LoRa nodes. Finally, we estimate the packet delivery rate at each position based on the signal power map from the path loss model. We show the coverage of standard LoRa, Falcon, and a cooperative transmission method named Quire. Falcon provides emergency links to disconnected clients, thus it extends the coverage area significantly compared with that of standard LoRa. Quire also extends the LoRa coverage by leveraging multiple cooperative transmitters, but it requires all the transmitters to send identical data, which limits its usage in real-world systems. The last question is about the outdoor performance of Falcon. We collect the LoRa packets from 10 positions at the campus and run our end-to-end system for packet detection and data decoding. As we can see, compared with the standard LoRa demodulator, Falcon decreases SER at all of the 10 positions. Most errors can be resolved by leveraging more retransmissions of each Falcon bit. This evaluation also proves that Falcon can provide reliable communication links to LoRa clients when the standard LoRa communication cannot reach. To conclude, in this paper, we propose the design, implementation, and evaluation of Falcon, a physical layer mechanism to provide reliable communication links for low SNR LoRa clients. The SNR gains enable longer communication distance and better coverage in LoRa. Of course, Falcon has some limitations as a future work. For example, the data rate provided by Falcon is much lower than that of standard LoRa, as Falcon leverages the whole packet for each bit transmission. So currently, we use Falcon as an emergency link mechanism to keep low SNR LoRa clients staying connected to the network in spite of the environment dynamics. Our future work has to optimize the interfering model to improve the data transmission efficiency. Okay, that's the end of the presentation. Thank you for your listening.